As we've seen, we can represent complex numbers in terms of either a rectangular manifestation with a real plus an imaginary part, or z equals a plus jb. We can also represent it in polar form, where we have an angle theta, an orientation from the horizontal axis, and the magnitude of the distance being the magnitude of z being the distance from the origin out to the point. And I've redrawn here the equations that relate the polar and rectangular coordinates. Changing from rectangular to polar, we have the magnitude of z is equal to that from Pythagorean's theorem, and the angle is that. And going from polar coordinates, where the coordinate values are magnitude of z and theta, back to the rectangular manifestation where the coordinates are a and b. So to go back to polar, we have a is equal to the magnitude of z cosine of theta, and b is equal to the magnitude of z sine theta. Now, let's write the complex number z in real form with a real part plus an imaginary part, but do it in terms of the polar coordinates. In other words, z then is equal to the real part a, let's write it like this, a plus jb, which is equal to, all right, a is equal to the magnitude of z times the cosine of theta plus j times the magnitude of z times the sine of theta. See what I've done? I've written it in rectangular form with a real part plus j times the imaginary part, but I've written the quantities in terms of the polar values of z, or mag z, and theta. Now let's factor out the magnitude of z, so this then is equal to, give myself a little more room, the magnitude of z times the cosine of theta plus j sine of theta. Now we look at that in brackets, that cosine of theta plus j sine theta, and we recognize that from Euler's formula as being e to the j theta. Thus, another way of writing z, this complex number, in its what we are going to refer to as its complex exponential form, which uses the polar coordinate values of magnitude z and theta. Thus, z is equal to magnitude of z e to the j theta. Why get so excited about this? In this complex exponential form, we can use all of the properties of exponents. In other words, say we had, let's just do it over here. Say we had one number, or one expression, 6e to the 3x, and we wanted to multiply it by 2e to the 1x. Well, we know that in doing this type of thing, you multiply the coefficients. 6 times 2 is 12. And because they're raised to the same base, we've got e to the 3x and e to the x. When you multiply e to the 3x times e to the x, you simply add the exponents. E to the 3x plus x is 4x. Similarly, if we wanted to divide 6e to the 3x by 2e to the x, you simply divide the coefficients. 6 divided by 2 is 3. And you subtract the exponents. 3x minus x is 2x, and we would have 3e to the 2x. So what we're saying then is that we can represent complex numbers in either rectangular form, a plus jb, or polar form, z, mag z, and theta, but that polar form is equivalent to, or can be represented in this complex exponential form, where we have the magnitude of z times e to the j angle of z. We're going to see that this form right here, this polar form, makes multiplying and dividing complex numbers very, very easy. And that's where we're headed now.